Okay, after a definite time or a certain time, this mass reached at this point, and at the same time this mass reached at this point, but this arc chop, or this distance and this distance not same, but they take same time, but they do not cover same distance. So they take this mass and this mass take same time, but not covered same distance. So that the velocity, the linear velocity will be different. But all over and each of the mass all over this body has the same angular velocity, but not same linear velocity. Okay, for mass m1, the linear velocity will be v1, and radius, suppose radius will be r1. For m1 mass, suppose this is m1, this is m1, this is m2, and this is the distance from the center. This is r1, this is r2. The m1 mass, the distance between the center and m1 is r1, and the distance between the center and m2 mass, this is r2, like this one, v1 r1, but omega same. For velocity v2, mass m2, omega r2. This is the linear velocity for m1 mass, this is the linear velocity for m2 mass. Okay. Now and this is the kinetic energy of m1 mass. This is the kinetic energy for m1 mass, half m1 v1 square. Okay, half m1 v1 means omega r1, omega square r1 square, omega square r1 square. Similarly, for m1 mass, this is the kinetic energy. For m2 mass, m3 mass, m4 mass, and then the total kinetic energy will be half m1 omega square r1 square plus half m2 omega square r2 square plus dot dot dot. Finally, half omega square, yes, half omega square, you make r1 square plus m2 r2 square plus dot. Equal to half omega square m1 r1 square m2 r2 square plus m3 r3 square. This is called I. We may present therefore here I means I equal to m1 r1 square plus m2 r2 square plus that means summation m r square, summation m r square. I mean summation m r square, okay, summation mi ri square or mr square I. Here I, okay, I, you know, E kinetic energy equal to half mv square. Here you can write half I omega square, half I omega square. You may also write this like this. Just rearrange like this. So equal to half I omega square. Very similar. This kinetic energy for linear movement and this kinetic energy for angular movement, for linear movement and for angular movement. Okay. Just instead of m there is I, and instead of v there is omega. V means linear velocity, omega means angular velocity. Out. Here I equal to summation mi ri square, mi ri square. So half mi v omega, v linear velocity and omega angular velocity, angular velocity. V linear velocity, omega angular velocity. M is linear mass. M is we may call M is linear mass. Then I should be angular mass. I should be angular mass. This is linear mass, this is angular mass. These are very similar equation for linear motion and angular motion. For linear motion, the velocity is linear velocity and mass is linear mass. And for angular movement, velocity is angular velocity and the mass is angular mass. I means angular mass. Rotational mass. M is linear mass, I is rotational or angular mass. I equal to summation m r square. I means I is called moment of inertia. Moment of inertia. This is I is called moment of inertia. Moment of inertia. M is linear mass, I is angular mass. This angular mass is called moment of inertia. Moment of inertia, because moment of inertia is a tendency to resist the angular acceleration, Angular acceleration means the chains, the rotational chains, it resists I. Moment of inertia means the tendency to keep itself unchanged. That means this I, or moment of inertia, resists the rotational chains or rotational acceleration. I. Okay. uh, moment of force and moment of inertia. Moment of force F into d, and moment of inertia m into r square. Torque means moment of force. I means moment of inertia. Moment of force F into distance, and moment of inertia mass into distance square. Mass into distance, that's okay. Mass into distance, force into distance. Mass into distance square, force into distance. Moment of force and moment of force and moment of inertia. Now question 13. Okay. Okay, this is a rod. This is a uniform rigid rod. This is a uniform rigid rod of length L and mass capital N, and it rotates about an axis and passing through O. Okay. And this is the axis. With respect to this axis, it will be rotated. This is rotating about the axis. Okay. Now this distance is L, and this distance is H. Then this distance will be L minus H. Now you have to derive the moment of inertia. You have to derive the moment of inertia of this uniform rigid rod. Of this total uniform rigid rod, you have to find out the moment of inertia. You know, moment of inertia I equal to mr square. Okay, mr square. Now to find out the moment of inertia of the total body, total rod, to find out, firstly you have to consider an infinitesimal mass. To find out through the calculus method, to find out the moment of inertia through calculus method, you have to first consider an infinitesimal or very small amount of mass. Suppose this is the very small or infinitesimal. Infinitesimal means অতি ক্ষুদ্র, হ্যাঁ, খুবই ছোট একটা ছোট, we have to consider an infinitesimal mass. Suppose this is the infinitesimal mass and the distance is dx, and this mass is away from the axis, x distance away from the axis. This mass, suppose this is dm, this is very infinitesimal mass dm. dm is the infinitesimal mass we considered, and x is the distance between